Now that we know what vectors are and we know how to perform some operations on them, we're going to take a look at some applications of vectors in the plane. We've already seen that vectors can be used to model quantities that have both size or magnitude and direction. There are a lot of real-world problems that, even though they occur in a three-dimensional world, can be modeled using 2 dimensions. And so we're going to see that we can use vector methods to simplify geometry, motion, and physics problems. We've already seen that the distance between 2 points is the same as the magnitude of the vector connecting those 2 points. Similarly, a simple application of trigonometry tells us that the direction of a vector is going to be equal to the inverse tangent of its vertical component divided by its horizontal component. We can model both displacement and velocity using vectors. A displacement vector, d, of the form delta x, delta y, gives us an indication of how far an object has moved in both the horizontal direction, delta x, and the vertical direction, delta y. Similarly, a velocity vector v equals v sub x, v sub y, tells us how fast something is moving in the horizontal direction, v sub x, as well as how fast it's moving in the vertical direction, v sub y. We can model force using vectors. The magnitude of a force vector is going to tell us how strong the force is, and the direction of a force vector is going to tell us at what angle that force is acting. We can then use these vectors to compute something called the resultant force when we have more than one force acting in more than one direction. The net force is just going to be the sum of the individual force vectors. Similarly, we can figure out when something is at equilibrium, or we can figure out a force we need to apply to it in order to keep it at equilibrium by noting that for something to be at equilibrium, its net or resultant force has to equal 0. Let's take a look at some of these ideas by examining a few examples. First, let's imagine an object that moves from the point P equals 2, negative 1 to the point Q equals 6, 4. And let's find the displacement vector that indicates that movement as well as the magnitude of that. So if we draw a quick sketch of those 2 points, 2, negative 1 is here, and 6, 4 is over here. So we can see that our vector looks like this. Our new vector, PQ, is going to be equal to the vector 6 minus 2, 4 minus negative 1, which is the vector 4, 5. The magnitude of PQ is going to equal the square root of 4 squared plus 5 squared, which is the square root of 16 plus 25, which is the square root of 41. Now, the question doesn't ask us to, but we can look at the direction of PQ. If we look at this triangle here, we know that this triangle has a vertical component of 5, because the vertical component of PQ is 5, and a horizontal component of 4. Because the horizontal component of PQ is 4, we're looking for the direction, which is this angle theta here, and we can see that the tangent of theta is opposite over hypotenuse in a right triangle, 5/4, which means that the angle is going to be the inverse tangent of 5/4. We can use a calculator real quickly and see that the inverse tangent of 5/4 is in fact, in radians, about 0.896 radians. If you want that in degrees, you can write it as 51.3 degrees approximately. Let's look at an example now that asks us to compare 2 forces. So here we're going to exert 40 pounds of force on a suitcase handle, and we want to know, are we going to get a larger horizontal component which is clearly the direction that we want to move our suitcase horizontally. If we have the handle at a 45-degree angle with the horizontal, or if we have the handle at a 60-degree angle with the horizontal. So each of these can be represented as a force vector. The 45-degree angle, we have a force with magnitude 40, and this angle here is 45 degrees. And we're looking to figure out the horizontal component. So in other words, we want to find this length here. We'll call that x. Well, that is adjacent to our 45-degree angle. So we know that the cosine of 45 degrees is going to be x divided by 40. In other words, x is 40 times the cosine of 45, which is the square root of 2 over 2. And so we see that x is going to be 20 square roots of 2. On the other hand, for the 60-degree case, we have a picture that looks very similar. But now we have a 60-degree steeper angle for our handle. We're still applying 40 pounds of force, so the magnitude of our force vector is still 40. We're still looking to find this component here. We'll call that x prime. So now we see that x prime, we're going to use the cosine of 60 is going to be x prime divided by 40. So 40 times the cosine of 60 is x prime. And the cosine of 60 is 1/2. So here we see that x prime is equal to 20. So the force is greater when we apply the 45-degree angle to the horizontal. Let's look at another force application. Here we have a 500-pound load suspended by 2 chains, each of which forms a 45-degree angle with the ceiling. So if we sketch a picture of this, it's going to look something like this, where we have our 2 chains and our load is hanging here. And if we orient the load so that it's at the origin of a system, we have some forces here. We have force 1 is this force right here. This is a 45-degree angle. So we can see from that that force 1, this is also going to be a 45-degree angle. And so force 1 is going to be equal to its magnitude times the cosine of 45, and its magnitude times the sine of 45. And its magnitude is ultimately the thing we're trying to find. So we can write that as the magnitude of F1 times root 2 over 2, the magnitude of F1 times root 2 over 2. F2 is going to be the force exerted by the second chain. And so we see that since that's in quadrant 2, where we still have a 45-degree angle here, because this is a 45-degree angle up there, but we're in quadrant 2, which means that our cosine is going to be negative. So F2 is going to be the negative of the magnitude of F2 times the cosine of 45. Sine is still positive in that quadrant, so we have the magnitude of F2 times the sine of 45. And so we get that F2 is going to be the vector negative F2, root 2 over 2, and then positive magnitude of F2, root 2 over 2. Our third force is the downward force created by the object itself. That makes a 270-degree angle, so that our third force, we'll call that F3. F3 is going to be the vector, the magnitude of F3 times the cosine of 270, the magnitude of that looks like a 5, F3, magnitude of F3 times the sine of 270, which is just the vector, the magnitude of F3. Now, remember that F3 is our weight, so the magnitude of F3 is 500. So this is 500 times the cosine of 270, which is 0, and then 500 times the sine of 270, which is -1. So we get F3 is the vector 0, -500. We know that our weight is not moving, which means we're in a state of equilibrium, which tells us that F1 plus F2 plus F3 is equal to 0, or in other words, F1 plus F2 equals -F3. Well, F1 plus F2 is going to be the vector F1, the magnitude of F1 minus the magnitude of F2 times root 2 over 2, the magnitude of F1 plus the magnitude of F2 times root 2 over 2. And that is equal to the vector -F3, which is the vector 0, 500. So now we know that the magnitude of F1 minus the magnitude of F2 times root 2 over 2 equals 0. That tells us that the magnitude of F1 and the magnitude of F2 are the same, which hopefully is fairly obvious to you from the picture. And we also get that the magnitude of F1 plus the magnitude of F2, this should have had parentheses around it, times root 2 over 2 is equal to 500. So here we get that the magnitude of F1 plus the magnitude of F2 is going to be 1,000 divided by the square root of 2. Those two quantities are equal to each other, so 2 times the magnitude of F1 is 1,000 divided by the square root of 2, which then tells us that the magnitude of F1 is 500 divided by the square root of 2, which is approximately 353.6 pounds. So the magnitude of the force of each chain, this answer right here, is approximately 353.6 pounds. Let's look at one last example here where we're going to examine velocity. So we have a sailboat that floats in a current, and the current is moving at a velocity of 1 meter per second due east. And then we have wind acting on the boat, which makes the boat's actual speed relative to the shore root 3 meters per second, but in a direction 30 degrees north of east. So we have a vector that represents the current. We'll call that C. That vector, since it's moving due east at 1 meter per second, the vector is going to be 1 for the horizontal component and 0 for the vertical component, since it's moving due east. We also have the boat speed, and that is going to be the vector root 3 times the cosine of 30 degrees, root 3 times the sine of 30 degrees. Because 30 degrees north of east means our boat vector this is 30 degrees north of east. So our boat vector is that one, but we know that the boat velocity is going to be the combination of the current plus the wind. And what we're looking for is we want to find the wind vector. So another way to write this is that the wind vector is going to be the boat vector minus the current vector. Let's rewrite our boat vector here. The cosine of 30 degrees is root 3 over 2. So here we get root 3 times root 3 over 2. And then we get root 3 times the sine of 30 degrees is 1/2. So the boat vector is the vector 3/2 root 3 over 2. So then our wind vector is going to be 3/2 minus 1, root 3 over 2 minus 0, which is the vector 1/2 root 3 over 2. The magnitude of that vector, which is going to be the speed of the wind, is going to be the square root of 1/2 squared plus root 3 over 2 squared, which is 1/4 plus 3/4, which is 1. Another way to write the wind vector is as the magnitude of the wind times the cosine of the wind angle, the magnitude of the wind times the sine of the wind angle, which means that the cosine of the wind angle, we're calling that theta, is 1/2, and the sine of the wind angle is root 3 over 2. Both of those tell us that the wind angle must be 60 degrees. So the speed of the wind is 1 meter per second, and the direction of the wind is 60 degrees, and that's going to be north of east. All right, we'll wrap this up with a quick summary of what we've seen here. We know that we can use vectors to model things like displacement, velocity, and force. We saw examples of each of those. We also saw that when we use the component form of a vector, it helps us to simplify our calculations because we can use simple addition, subtraction, things like that to equate forces to one another. The magnitude of the force is a physical meaning. We saw that it could represent the weight of a load, the speed of a boat, things like that. And so we'll note that vectors are incredibly useful with applications across science and engineering.